So we're looking at forces and equilibrium. When a system is in equilibrium, we say the net force is zero, so resultant overall force is zero. And this means the object is either at rest or it's moving at a constant velocity. Because from F equals ma, where F is the resultant force, if that equals zero, then the acceleration equals zero. So a system that is in equilibrium is not accelerating. If you have two forces acting on an object and that object is in equilibrium, then these two forces have to be equal in size and opposite in direction for the net force to be zero. If you have more than two forces, then if the sizes and directions of the forces when they add together form a closed loop, then the system is in equilibrium. So if we consider the three forces here, A, B and C, and if we were to add them together, so a head to tail of A plus B plus C, and they're forming a closed loop because C has ended where A has started, then we can say that the resultant force is zero, and so these three forces are making the system in equilibrium. We can also show that the resultant force is zero if we resolve the forces, i.e. resolve for B and C. So if we first consider B, which is acting to the right and upwards, so it has a horizontal component to the right and a vertical component upwards. And then if we consider C, which is acting to the left and upwards, so it's got a horizontal component to the left and a vertical component upwards. So B can be replaced by BH and BV, and C can be replaced with CH and CB. So now let's consider the vertical components where we add A with BV and CV. You can see that vertically the resultant force is zero. So our A is equaling our BV and our CV. We now consider horizontal components and we add BH and CH. Again, we can see that the resultant force is zero. So our BH equals our CH. So both vertically and horizontally, the resultant force is zero. So overall, the resultant force is zero. So the system is in equilibrium. Let's now consider these three forces. And if we add them together, if they form a closed loop, then we can say the forces are in equilibrium. So because there's three forces, the closed loop will form a triangle. So how we would create this triangle of forces, let's start with the easiest force to draw, which is in this case our vertical force. So our 1.5 newtons acting down. And then to add the next force, again remember it's the head to tail, so where the first force ends is where we start the new force. So we'll add on the red force of 1.2 newtons, but it's acting 60 degrees from the horizontal. So let's draw a horizontal line, and then we need to draw the 1.2 newton force, but at an angle of 60 degrees relative to the horizontal. Finally, we're going to add the blue force, our 0.75 newtons. This acting 30 degrees from the horizontal. So where our 1.2 newton force has ended, we need to draw a horizontal line. And then from there, we can add on our blue force of 0.75 newtons, but an angle of 30 degrees relative to the horizontal. And looking at the Z angles, just to complete this angle, we can use the rules of maths and Z angles. Because this angle is 60 degrees, then this angle here is also 60 degrees. So the total angle between the blue and the red forces is 90 degrees. what we can see is that these three forces are forming a closed loop, a triangle, and so we can say that the resultant force is 0 and that the system is in equilibrium. So here's another example of three forces that are acting so the system is in equilibrium. So we've got a vertical force downwards of A, got a horizontal force to the right of B, and we've got a 50 Newton force acting 30 degrees from the horizontal and acting in upwards and towards the left direction. We're going to add these three forces to form a triangle. So let's first consider A, which is acting downwards, and where A ends, we will add B, acting horizontally to the right, and where B ends, we're going to add our 50 newtons, but it's going to be acting 30 degrees relative to the horizontal. So you can see they're forming a closed loop, so we can say the forces are acting so that the system is in equilibrium. If we now need to find B, for example, we can see that relative to the angle, B is the adjacent and the 50 newtons is the hypotenuse. So we've got an adjacent and the hypotenuse. So to find B, if we take the horizontal component of the 50 Newton force, that is going to equal B. And that would be found by 50 cos 30. And you can see from the example that if we was to resolve the 50 newtons to find the horizontal component, then you can see horizontally FH must be equal to B. Now to find force A is opposite to our angle, and again the 50 newtons is our hypotenuse, so we've got opposite and a hypotenuse, so we need to use sine. So A would be found by the vertical component of our 50 newton force, so A would equal 50 sine 30, and you can see that if we resolve our 50 Newton force to find the vertical component, then we can see that our vertical component must equal A. So here we have another example where we have three forces acting so that the system is in equilibrium. So we've got a vertical force downwards of X, and we've got two 50 Newton forces that are acting at an angle of 25 degrees from the horizontal. So first we're going to draw a triangle of forces. So we'll draw the easiest force first. So that's going to be our vertical force X acting downwards. And where force X ends, we're going to add this 50 Newton force. But we need to draw it at 25 degrees from the horizontal. So we need to draw a horizontal line where force X ends and then draw the force 50 newtons 25 degrees from that horizontal line. We then need to add off the other 50 Newton force, which again is acting 25 degrees from the horizontal. So where this 50 Newton force has ended, we need to draw another horizontal line here, and then we need to add our 50 Newton force at an angle of 25 degrees from the horizontal. And if we are to complete this angle here, you can see again using the rules of maths and Z angles that if this angle is 25, then this angle here must be 25 degrees as well. So the total angle between the 50 Newton forces is 50 degrees. And if this angle is 50 degrees and this angle is 65 degrees and all the angles inside a triangle must make 180, well then this angle, the final angle missing, is 65 degrees. If we need to find X, we could use either the sine rule or the cosine rule. But I'm going to use the sine rule first. So what we would take is the length X and divide it by the sine of its opposite angle. So it would be x divided by sine 50, and that will equal to the 50 Newton length divided by the sine of its opposite angle, which is 65. And rearranging, that will give x equals 42.3 newtons. Using the cosine rule, where we've got a squared is our length, which we'd say is our x, and that equals to b squared plus c squared, our lengths of b and c, which are both 50 newtons, minus the product of 2 and b and c, and cos of a, where a is the angle which is opposite to length a. So in this case, our angle A would represent our 50 degrees. So if we were to substitute those values in, where B equals 50 and C equals 50 and our A equals 50 degrees, that will all equal our x squared. And if we then put this into our calculator and take the square root, we'll get the same answer we got when we use the sine rule, where x is equal to 42.3 newtons. An alternative way to find x is by resolving the forces for the 50 Newton forces. If we first look at the horizontal forces, because they are acting in opposite direction, their components, they balance out, so we can ignore them. And then if we look at the vertical forces of the 50 newtons forces, they're both acting upwards, vertically upwards. And so we can say the two vertical forces will add together to equal our x. To find our vertical components, we can see it is opposite to our angle, and our 50 newtons is representing our hypotenuse. So we've got opposite and hypotenuse, so that means we will use the sine term. So FV will be 50 sine 25. And because there's two of them, if we add them together, as we say, that will give us our x. So we can say our x is equal to 2 times our 50 sine 25. So again, as we've shown with the sine rule and the cosine rule, and now with resolving, that x equals 42.3 newtons. So this animation is showing the weight acting on an object when it's on a horizontal surface. But if the surface was at an incline, what you can see is that the weight of the object, represented by the orange line, it has components which are parallel to the slope given by the purple and perpendicular to the slope, the surface, given by the blue. And if we increase the angle, the component that's parallel to the slope increases. And the syllabus expects you to be able to resolve the component of weight into the forces that are parallel and perpendicular to an incline slope. And that's what we're going to look at next. Let's consider this example of a car moving at a constant velocity up an incline plane. And because it's moving at a constant velocity, it's not accelerating. So we can say that the resultant force acting on the car is 0. And we've got 3 forces acting on the car. We've got its weight acting vertically downwards. We've got the normal reaction force acting on it due to the surface. And we've got the forward force acting on the car, which makes it move at constant velocity up the slope. So in this case, rather than looking at horizontal and vertical components, it's easier to look at components parallel and perpendicular to the slope. For that reason, we will need to resolve our weight into components that are parallel and perpendicular to the slope. So if we consider these components of weight, so we've got the perpendicular force component of weight, which is opposite to the normal reaction force. And we've also got the parallel component of weight, which is opposite to force F. So these two components can replace our one component of weight. Our component of weight is making an angle theta from its perpendicular component, and this angle theta is the angle of the incline of the slope. Now, why are these angles the same? Well, if we consider the triangle made by the slope, the horizontal, and the weight force, and you can see the weight force is making an angle of 90 degrees with the horizontal. So we've got 90 degrees and theta. So the remaining angle in the triangle must be 90 minus theta. So this angle represents the angle between weight and its parallel component. And we know that the parallel and perpendicular components are 90 degrees away from each other. So if this angle is 90 minus theta, then the angle between weight and its perpendicular component must be theta. So now what I'm going to do is resolve the components of weight into the parallel and perpendicular components. So if we consider the perpendicular component first, so you can see this component is adjacent to angle theta. Our weight mg is representing the hypotenuse, so we've got adjacent and the hypotenuse, so we need to use the cos term. So our perpendicular component will be mg cos theta. To now find the parallel component, this line is the same as this line here, and you can see that this line is opposite to the angle, and again so we've got an opposite and we've got the hypotenuse of weight. So opposite and hypotenuse means we need to use the sine term, so the parallel component will be given by mg sine theta. So as I said before, we can now replace our weight with our perpendicular and parallel components. So if we look perpendicular to the slope, we can see that our normal reaction must equal to the perpendicular component of weight, so n equals mg cos theta. And parallel to the slope, force F must equal the parallel component of weight, so that is mg sine theta. So we can also show that the overall force is 0 by drawing a triangle of forces. So I replace the perpendicular component with n and the parallel component of weight with F. So we're adding our weight, then force F, and then force N. It's forming our closed triangle. So we can use trigonometry to find N and F. So if we first try and find N, you can see that it's adjacent to angle theta. So we've got adjacent and we've got the hypotenuse of weight. So that means we can use the cosine term. So N will equal mg cos theta. To find F, we can see that it is opposite to angle theta. So we've got opposite and the hypotenuse, which means we can use the sine term. So F will equal mg sine theta. So alternative, what we could do is we can rotate the incline by an angle of theta so that the incline is now horizontal. And so if we go back to the previous line, if we also then, as a result, we can rotate our triangle of forces. So F is now acting horizontally, normal reaction is acting vertically, and our weight is acting at an angle of theta from the vertical. And then again, we can just use normal trigonometry to find n, to show it equals mg cos theta, and to find f so that it equals mg sine theta.